Hi, everyone. Good morning and welcome back to 124103. Can you please just confirm that you can hear me clearly and you can see the PowerPoint slides that I'm sharing? Okay, good. Thanks. Thanks for the confirmation. So yeah, I hope you were able to have a good, nice break over the Easter and Anzac holidays and the mid-semester break period. And hopefully you're ready to engage in the second half of 124103. Yeah, so in today's lesson, we'll pick up from where we left off from last time. So we will still talk about fluids, this time talking about fluid dynamics. So when we say dynamics, then the fluid starts to flow. So just before we went on a break, we already started talking about fluids, but we were talking about fluids in general, right? Being the objects that are free to flow, which refers to both liquid and gas phases of matter. And before the break in lecture 12, we just defined some terms and properties that fluids have in general. So for example, density being mass over volume, and the pressure that the fluid experiences being force over the area over which the force is exerted. And then we talked about different kinds of pressures, gauge pressures, and the total pressures. And then we talk about buoyancy being related to the change in pressure with depth. So before the break, we talked about the general properties of fluids, and these properties could be when the fluid is static, when it's not moving, or when it's already moving. So that's the object of lecture 13. We will now cause the fluid to flow. And so we have fluid dynamics. And we'll talk about these concepts here in the learning outcomes. And of course, when fluids flow or the movement of fluid is important in many applications, especially in physiology. So our approach for today, we'll talk about fluid flow, the general concepts of it using the flow of water through a pipe, to talk about the general concept of fluid flow. And then we will apply those general concepts to physiological examples, for example, the flow of blood in the artery or in capillaries. Okay, so that's the plan for today. So when we say fluid flow, we can define a quantity called flow rate. Okay. Flow rate, which we give the symbol capital Q, and later on mass flow rate. So let's talk about flow rate, or Q, first. When we say flow rate, strictly speaking, what we mean is volume flow rate. But you won't hear us saying the word volume anymore. So when we say flow rate, it's implied that we're referring to volume flow rate, and that means it's the volume of fluid that crosses an area. Yeah, the volume of fluid that crosses an area in a given time. So if you put that into an equation, so this is the general definition of flow rate. It's the volume of fluid that crosses an area in a given time. Put that in equation form, then you have this Q representing flow rate is equal to volume over time. So delta V there refers to the volume of fluid that crosses an area at any given time. So Q is equal to volume over time. And if you think about a pipe, right, say a cylindrical pipe like so, and you think about the volume of fluid that's flowing through this pipe, it's probably by intuition, we can intuit that the volume of fluid flowing through the pipe would depend on how big the pipe is, right? So if you have a bigger pipe, if you have a big pipe, like so that the cross-sectional area of the pipe is big, then of course more fluid is able to flow through this big pipe as opposed to when you have a smaller pipe, so that the cross-sectional area of the pipe is small, like so, right? So the flow rate would also depend on the area, the cross-sectional area of the pipe. And it also depends on how fast the fluid is flowing through the pipe, right? Because if you think about it, if you have, say, this pipe of some cross-sectional area A, okay, a pipe with a certain size, if the fluid flows so quickly through this cross-sectional area, then you have a lot of fluid flowing through this area at any given time, as opposed to when the fluid flows slower through this cross-sectional area, then the flow rate would be smaller as well, right? And so we can also have another useful form for flow rate being the cross-sectional area of the pipe or the thing where the fluid flows, cross-sectional area times the speed of the fluid, right? So we have these two forms of equations that define the flow rate. The first one referring to the amount or the volume of fluid crossing an area at a given time. And the second form is probably the more intuitive one, which relates the dimension of the pipe in the form of cross-sectional area and the speed for which the fluid is flowing. Yeah, so which equation to use just depends on what is what you know, what is given in the problem, and what you want to find out, or what's being asked. In terms of the unit for flow rate, because the basic definition of flow rate is the volume of fluid that crosses per given time, the unit will therefore be the unit for volume. Okay, so in terms of the unit, you have the unit for volume is cubic meter, and the unit for time is seconds, and therefore the unit for flow rate is cubic meter per second. Right. Okay. Sorry, let me just arrange my screen so I can see the chat and participants boxes. All right. Okay. Good. So that's volume flow rate, or just simply flow rate Q. Now, in terms of mass flow rate is it's a similar. It's essentially the same concept. It's the amount of fluid crossing at a given time, except that in this case, in the case of mass flow rate, instead of considering volume as being how much, we consider the mass of the fluid that's crossing surface in a given time. So mass can be expressed in terms of density. Recall last time in lecture 12, when we defined density is defined as mass per unit volume. And if we rearrange this equation, which we did last time, then we can have the relationship mass is equal to density times volume. So mass flow rate is just essentially flow rate, but written in terms of mass and therefore density. But it's essentially the same concept. It's the amount of fluid. It's the amount of fluid crossing a surface at a given time, except that we express how much as mass and then density. And so we have this equation for mass flow rate. Instead of volume, we replace volume with mass. So M here represents mass per given time, and you have density times the area times the speed. Okay, now consider, for example, a pipe that changes its cross-sectional area. For example, as shown in this figure, you have a pipe with a certain cross-sectional area A2, and then at a certain point, the pipe narrows such that A1, the cross-sectional area at this point, is smaller than the original cross-sectional area. Conservation of mass says that what goes in must come out. So the amount of fluid going into the bigger area needs to come out at the smaller end of the pipe. Okay, and so what happens, as illustrated by this blue shading here, okay, because you have a bigger cross-sectional area, the fluid can be distributed over a bigger cross-sectional area, and you only have this much fluids over that bigger cross-sectional area. But when the same amount of fluid encounters this smaller cross-sectional area, they're sort of squeezed into a smaller cross-sectional area, and so they extend over a longer length over that smaller cross-sectional area. But the amount of fluid in this part should still be the same as the amount of fluid in this second part, in the smaller, with a smaller cross-sectional area. Okay. And so that's the idea behind continuity equation. It's essentially saying that the amount of fluid at one point of the pipe should be the same amount of fluid at a second point in the pipe, even if the size of the pipe changed. Okay, so putting that definition in equation form, okay, then we can write continuity equation as the mass flow rate through cross-sectional area A1 being equal to the mass flow rate through cross-sectional area A2. Okay. Right, and mass flow rate, we defined that in the previous slides as density times area times V1. If you go back to our definition for mass flow rate, you have density times cross-sectional area times the speed. So the mass flow rate, where the area is A1 and the speed of the fluid is V1, should be the same as the mass flow rate when the area is A2 and when the speed of the fluid is V2. Okay, for fluids where the density can change, then the density at cross-sectional area A1 can be different to the density at cross-sectional A2. But for most fluids, the density is constant, right? If water comes in to this part of the pipe, it's also the same water that comes out of this part of the pipe. And the density of water is the same regardless of whether it's in a narrow part or in a wide part of the pipe. So we call those fluids incompressible. When the density of the fluid is constant, we call them incompressible. And I think in this course, we will mostly deal with incompressible fluids. That means that the density is the same all throughout the flow. And therefore, density at both sides of the equation, of the continuity equation, cancels each other out. And so you only have this relationship between the cross-sectional area and the speed of the fluid at one part of the pipe and at another part of the pipe. Okay. So this form of the continuity equation is probably what we will be using quite a lot in this course, where we consider incompressible fluids. The important implication of this equation is that the narrower the constriction, or the narrower the smaller the cross-sectional area, the faster the fluid flows through it. And yeah, so if we look at this illustration here, you have A2 is a wider cross-sectional area, the velocity vector is smaller. The fluids flow slower here. At the constricted part, narrower part, the fluids flow faster. It's a little bit, yeah, it takes a bit of time to get around this concept, but maybe if we put numbers, it's easier to imagine how the speed of the fluid changes if the area, cross-sectional area changes. So say, for example, we're given that the area, so that's a bigger area. So so for example, area 2 is equal to 10 square meters, and the speed of the fluid at this cross-sectional area is, say, 2 meters per second. Then using the continuity equation, A2 times V2, or the cross-sectional area times the speed of the fluid, is simply 20 meter cube per second, right? It's essentially just multiplying the cross-sectional area with the speed. So that's 10 times 2, which is 20 cubic meters, which means every second, 20 cubic meters of fluid is flowing through this cross-sectional area at the left end of the pipe. So say at the narrower end, so say A1 narrows down to, for example, 5 square meters, right, at this right end of the pipe. Then the left side of the continuity equation says A1 multiplied with V1 is equal to 5 multiplied with whatever, we don't know, right? We don't know the speed of the fluids at this narrower area A1. Okay, but we know from continuity equation that 5 multiplied with V2 should be equal to 20 cubic meters per second, because whatever value A2 V2 is, that should also be the value of A1 V1. Right? Does that make sense? Okay, right, but A1 V1 should be equal to 20 cubic meters per second. And so V1 should be equal to 4 meters per second in this case. Right. Because if you multiply 4 with 5, you get 20, which is the same as A2 V2. So that, yeah, A1 V1 5 times A1 5 times 4 should be equal to A2 10 times 2. Okay. Right. So the narrower the constriction, the smaller the cross-sectional area, the faster the fluid should flow through it. Yeah. Does that make sense? Yeah. Okay, good. Yeah. Yeah. Sometimes you can think of it as like it's so narrow, it's so constricted that the fluid needs to flow faster so that it can accommodate all of the fluid that needs to flow through this narrower section of the pipe. Yeah, and a good analogy of this is Hookah Falls. So if for those who've been to Taupo and who have seen Hookah Falls, okay, right? So notice as we go further and we're able to view the fluid flowing through this narrow, so the narrow where the bridge is narrower. Okay, let me just pause that right there so we can see what's happening here. Oh, I'm not able to write. Let's see if I can write and annotate through here. Yeah. So notice how in this section of the channel or section of Fuka Falls, you have a narrower section as opposed to this part here, wider. Okay, and notice how at the wider part, the water seems to be calmer because the water is flowing slower, and you have this calmer area where the falls is wider. And then as you have this narrower channel here, water starts to flow faster, and if you've been to Hookah Falls, you would have seen this directly, that the water does flow very fast where the bridge is, where you have this narrower section. And so that's this is like an example of continuity equation, where the amount of water in the wider area should all squeeze through this narrower area, and for the same amount of water to squeeze through the narrower area, the water needs to flow faster through the narrower area. Right. Okay, so just think about Hookah Falls is probably a good analogy for the continuity equation. All right. Okay, now let's look at some numerical examples, like examples of questions that we might use continuity equation. Okay, so here, for example, we have a water pipe and it carries 1,000 liters of water per minute into your street. If the speed of water is 2 meters per second, then we want to calculate these things: the flow rate, cross-sectional area of the pipe, and the radius of the pipe. And then at one point, the pipe narrows by 10%. The radius of the pipe narrows by 10%, and we want to calculate the new speed of water. So I've written down here some answers. So if you want to try this out, then yeah, you can try solving these questions and then check your answers against these answers. But we'll go through the solution of this question as well. We'll just first dissect the problem. So 1,000 liters is a unit for volume. So in short, 1,000 liters, you're given the volume of water that's flowing through the pipe. Minute, of course, is a unit of time. Okay. So you're also sort of given the time, because it's like 1,000 liters every minute. It's essentially saying 1,000 liters every 1 minute. Okay, so the time there is 1 minute. And you're, of course, given the speed, meters per second. Just looking at the units tells you that that's the speed. All right, so flow rate, the basic definition of flow rate is, the volume of fluid that crosses at a given time. So that will be volume divided by time. Volume. Yeah, and we've seen we're given the volume, it's 1,000 liters, and the time is 1 minute. 1,000 liters of water is crossing an area every minute in 1 minute, every minute or in 1 minute. Now, the thing here is we have to use base units. So liters is not the base unit. The base unit is cubic meter. And minutes is not the base unit for time. It has to be in seconds. So we have to convert liters to cubic meters and minutes to seconds, right? So the conversion factor from liters to cubic meters is shown here. 1 liter is 10 to the minus 3 cubic meters. So if we convert 1,000 liters, we can write that as 1,000 times 1 liter. Okay, and using our conversion factor, 1 liter is equal to 10 to the minus 3. So we simply replace 1 liter with our conversion factor, which is 10 to the minus 3. So you have 1,000 liters should be 1,000 times 10 to the minus 3 cubic meters. And then for the time, 1 minute is equal to 60 seconds. So we don't have to do much except that know the conversion factor for time. Right, so we have there now the volume converted to cubic meters. And you have the time converted in seconds. Then we carry out the operation using, using your calculator, then you should get 0.0167 cubic meters per second. So every second, there's 0.0167 cubic meters of water flowing through that pipe at a speed of 2 meters per second. All right, does that make sense? Are we happy with the solution for the flow rate? Good. Yep. The conversion factor from liters to cubic meters will be very useful when we're talking about fluids, because commonly we give volume in terms of liters. So this is one thing you might want to put in your formula sheet for the exam, is that conversion factor there. Okay, and now the next question, we want to find the cross-sectional area of the pipe. So we assume that so from the previous question, we solved for the flow rate. Okay. And we know that flow rate is also related to the cross-sectional area of the pipe times the speed for which the fluid is flowing through that area. Okay, as we've seen in the earlier slides. So we've solved for flow rates and we are given the speed. So 2 meters per second, that's the speed. That means we need to rearrange this equation to isolate isolate the area. Okay, area is being multiplied with volume. So if we divide, with speed. So if I divide the both sides with the speed, then speed cancels out on the right side, and we have the area is equal to flow rate divided by the speed. And we're given the flow rate. We're given the speed, 2 meters per second, and the flow rate we've calculated from the previous question. And so we're able to find the area to be, if you use the rounded flow rate, then you'll get 8.35 times 10 to the minus 3 square meters. I would suggest using the unrounded flow rate, so you have an area of 8.33 times 10 to the minus 3, because we will be using this area in the succeeding questions. So to avoid carryover errors or carryover uncertainty, we'll just use 8.33 times 10 to the minus 3 square meters. All right. Okay, are we happy with the solution for the area? Okay, yep. Okay, next question, what's the radius of the pipe? So the pipe, it's cylindrical. And remember, the area we're talking about is the cross-sectional area. Okay, oh, sorry, there's a question. So there's a question. 1,000. Yes, that's right. So you're right, Oksana. 1,000 times 10 to the minus 3 is also equal to 1. Okay, you're exactly correct. 1,000 times 10 to the minus 3 is also equal to 1. So when you do 1 divided by 60, it's 0.0167, which is also the same answer that we got. So yeah, so your answer is actually correct. It's the same. So you did not make any mistakes. Yeah. Yeah, okay, good. Okay, so next, next question, radius of the pipe. So no, that's okay. That's okay, Oksana, no problem. So the pipe is cylindrical, and we're just looking at the cross-sectional area because the water is just flowing through this cross-sectional area. It doesn't matter whether the pipe is long or short. It's really just how big the mouth of the pipe is that determines how much fluid is flowing through the pipe, right? And so to get the radius of the pipe, notice that if you look at one end of a cylinder, okay, you'll see a circle. So the shape of the cross section of a cylinder is a circle, okay, and the area of a circle, the cross section is a circle of radius r, and the area of the circle is pi r squared. Right, so this is also probably one useful information you'd want to put in your formula sheet, because when we go, for example, to arteries or veins or capillaries, we'll also consider them as, model them as cylinders, and so their cross-sectional area would also be circular. And the area of a circle is pi r squared, where r is the radius of the circle. So from the previous question, we found the area, cross-sectional area. And now we want to find the radius. So we need to rearrange this equation to isolate for r. Okay, so notice r is squared. So it's raised to the power of 2. Before you can do anything to remove the exponent 2, you need to get rid of pi, because pi is being tied to r via the multiplication sign. If we go back to the basics of rearranging equations and we build the equation up using the order of operations BEDMAS, okay, I hope you still remember this. You do the brackets first, then the exponents, then division, multiplication, addition, and subtraction. So if we build the equation up, starting with what you want to rearrange, what you want to isolate, which is r. Okay, then you do the brackets first, but there's no bracket in the equation. Next, you do the exponent. So to build up the equation, you need to do the exponent okay, raising r to the power of 2. And then you do the multiplication with pi. So you have pi times, let me just remove pi r squared. Right, so that tells you that when you rearrange, and then you have the equation A. So that tells you that when you rearrange your equation, you have to divide by pi first, okay? You have to divide by pi first, and then, so you have A divided by pi, and then you do the reverse of exponent 2. So what's the reverse operation of exponent 2? it's the square root, right? So the reverse operation of the exponent 2 or raised to the power 2 of 2 is square root. Okay. Okay, and so if you rearrange, if you want to do the rearranging the shorter way, okay, that means you need to get rid of pi first by dividing both sides with pi. So you get rid of pi and you have a over pi on the left side and you have r squared on the right side. Then you have to then get rid of the square by doing the square root. Okay. And therefore the rearranged form for r is equal to square root of a over pi. Right. Okay, from there, if you get the correct rearranging, it's just a matter of substituting the numbers. Yeah, sorry, this is exponent -3. It's not -3. So that's 8.33 times 10 to the minus 3 divided by pi, and then get the square root, and that should give you a radius of 0.0515. All right. Are we happy with the solution for R, especially for the rearranging? Okay, yep, good. So the rearranging bit is the crux of the problem here. Yeah, you'll do, I'd say this rearranging for R would be quite common. So yeah, either you put this in your formula sheet, or if you do this rearranging many times, then it becomes easier as well. Now, the last question, if the radius narrows by 10%, calculate the new speed of the water. A continuity equation tells us that if the radius decreases, then the area decreases as well, because the area depends on the radius, and therefore the speed should change. Now, the radius from the previous question is 0.0515. Okay, it narrows by 10%. Narrows by 10% means that the radius decreases by 10% of the original radius, right? Right? Okay, narrows by 10% means that the original radius decreases by 10% of whatever it is. Okay, if you put like 10% of 0.0515 in equation form, okay, 10% also means 10 divided by 100. Okay, of means multiplication. And then, of course, 0.0515, that's the original one. So if you put 10% off something in equation form, that will be 10 divided by 100 times whatever you're wanting to get 10% off. Right. Okay, so that will give you 0.00515 meters as 10% of 0.0515, the original radius. So therefore, the new radius will be the original radius minus the 10%. Okay, and that will be 0.04635 meters. Okay, does that make sense? Okay, sometimes thinking in percentage can be a little bit confusing. But yeah, hopefully this makes sense. Yeah, good. Thanks for the thumbs up. Okay, so we know our new radius. Our new radius is here. Then we can calculate the new area. So again, a circle the cross-sectional area is a circle, so the new area is pi r squared, but we'll use the new radius, the radius that narrowed by 10%, and we get this new area. From the new area, we can use the continuity equation, the area times the original area times the original speed is equal to the new area times the new speed. We want to find the new speed. Okay, so we rearrange this equation. If we divide both sides with, so we want to isolate the speed, and so we divide both sides by the new area, so that new area is canceled out, and we have this rearranged equation for the speed. And it's just a matter of substituting the numbers. Again, another correction, don't know why. Yeah, the format is being changed here, but yeah, that's times 10 to the minus 3. So that's an exponent of minus 3, not not a subtraction. Okay, so the old area, which we calculated from before, times the old speed, 2 meters per second, divided by the new area, gives you a new speed. So you can see that when the area decreased, the speed increased, because of the continuity equation. All right. Are we happy with that solution and using the continuity equation to find the new speed? All right. Okay, now let's apply the continuity equation to a physiological problem. Here, the area of the artery decreases by 33% because of some blockage, maybe cholesterol blockage or something. So the area of the artery, it's now the area, it's not the radius. Okay, it's area itself that's given to decrease by 33%. Then by how much will the speed of the blood in that artery has to increase by? So we've already seen that if the area decreases, then the speed should increase, right? So but by how much will the speed increase? Okay, we start with continuity equation. So that's the problem there. The continuity equation says that the flow in the normal artery should be equal to the flow in the narrowed artery, right? Or A1V1, 1 being the normal artery and is equal to A2V2. The subscripts 2 refer to the narrowed artery. Okay, so we have to figure out how much the new area is, okay, relative to the original area. What the problem just tells us is A2 is 33% smaller compared to A1. Okay, so using what we talked about earlier in terms of percentages. So decreased by means you're subtracting, right? So this is decrease by, okay, decrease by 33%. So 33%, when we say 33%, it's 33 divided by 100. So this term here is the 33% in the problem of the original. So A1 is the normal area, right? So the new area is the normal area minus the 33% of the normal area, because the new area decreases by 33% of the original or normal area, right? Okay, so what we did here is we wrote the sentence, like the sentence, into the equation form. Okay, yeah, And I hope that makes sense. So just a little bit of confirmation there whether this equation makes sense. Yep. Okay. Good. All right. Okay, so then the new area will be A1, that's still the same, minus just 33 divided by 100 is 0.33 times A1 still. Now, if you have this equation where you're adding or subtracting, and you see that there's a common variable in each of the terms in your addition or subtraction equation, then you can do what we call factoring out. So notice in the right-hand side, you have A1 appearing on both the subtraction terms. So we can factor out A1. If you factor out A1, take it out of both terms, we have 1 minus 0.33 times A1. Okay, so this tells us, this mathematical trick or rule tells us that if you're multiplying something to a bracket, then you multiply that thing to each term in the bracket. So if you multiply A1 to each term in the bracket, then you should be able to reproduce the original equation. So you have A1 times 1 is equal to A1 minus A1 times 0.33 is equal to 0.33 times A1. So that's how you know that you've factored out A1 correctly. Okay. But by factoring out A1, we are able to simplify the equation, because then you only have numbers inside the bracket. 1 minus 0.33 is 0.67. Okay. So that means A2 is equal to 0.67 multiplied with A1. Right? Okay, so this is how the areas are related. So we can now go back to our continuity equation and substitute out A2. Okay, so notice how A2 here, we just replaced that with 0.67 times A1 because we've determined that A2 is equal to 0.67 of A1. Right, and then we can rearrange this equation to isolate V2 by dividing both sides with 0.67 multiplied with A1. Right. Okay, V2 is therefore A1 times V1, the left-hand side, divided by 0.67 times A1. Okay, notice how A1 appears on both sides of the denominator bar, right? And any number divided by itself is equal to 1, which means A1 divided by A1 is equal to 1, which equivalently means you can just cancel A1. And you are left with V1 divided by 0.67, or you have 1.5 times V1. Yeah. So 1.5 came from 1 divided by 0.67. Essentially, you have V2 is equal to 1 divided by 0.67 times V1. If you separate out the numbers from the variable, from the letters. Okay, which means that the increase in speed is 50%. Right? Notice that you can also write 1.5. You can write that as 1 plus 0.5 times V1. Okay, yeah. Right, so you have V1 plus half of V1. If you do the distributive law, you have V1 plus half of V1, right? So the new speed is the original speed plus half of the original speed, and that's why the new speed increases by 50%. Right? Okay. Does that make sense? Are we happy with the solution for V2? Yep, good. Okay. All right, so the continuity equation tells us, so this figure here, it's essentially just continuity equation, continuity principle, the figure on the left. So we've seen that if the area changes, then the velocity or the speed of the fluid changes. So here, bigger area, you have low speed, and here, smaller area, you have high speed. When the speed changes, the pressure of the fluid will also change. When the speed is low, the pressure is high. So low speed means high pressure, and high speed means low pressure. One way to think about this is like if you have a big area, if you have a big cross-sectional area, so you can think about your water molecules or your water particles can like move about slower. They move about slower, and they have more opportunities to hit the walls of the pipe, right, at this point. And because they're hitting the pipe more often, they're exerting force on the pipe, and therefore you read a higher pressure at this point where the fluid, or let's say water particles, are moving slower. But when they encounter this narrower area and they move faster, they're sort of more directed. Okay. The water particles are more directed because they have this goal of passing through this narrow area, and so they have less opportunity to hit the walls of the pipe, and therefore you will measure a lower pressure because there's less force exerted by the water particles on the walls of the pipe. So you can think about it that way, why when the fluid flows faster, there is lower pressure, and when the fluid flows slower, there is higher pressure. Okay. In terms of pressure, we also learned last time that if the height or the depth of the fluid changes, the pressure also changes, right? We learned in lecture 11 that the deeper you go, the higher the pressure, because pressure being force, pressure is defined as force over area. The deeper you go, then you have more air particles pressing downwards, so you have a higher force that's contributing to a higher pressure the deeper you go. Okay? And so pressure is affected by both the depth or the elevation of the fluid, and it's also affected by the speed of the fluid. And putting the effect of both elevation and speeds together, we have what we call Bernoulli's equation. So Bernoulli's equation tells us how the pressure changes when the elevation or depth and the speed changes in the pipe. This is this very long equation here. Okay. Yeah, I can sort of, I don't see your faces, but in a real class where I see my students' faces, I often see panic in their faces. But we will go through this equation, this rather long equation, and see how we deal with such an equation. But here I just define what each of the terms mean. Be careful here, you have capital P and then you have this rho. Okay, so again, this is like the curly or fancy P, rho, which refers to density. Okay, it's different from P, which refers to pressure. Okay. And then you have speed for V and height for Y, height, elevation, or depth for Y. So how we interpret Bernoulli's equation, let's look at two cases. Okay, so the first case is when the fluid is static, meaning there is no flow, but the elevation changes. Okay, right, so in this case, V1 and V2 should be equal to 0 because the fluid's not moving, so speed should be equal to 0. So this term would disappear. That would be equal to 0, but anything you multiply with 0 is equal to 0. And this term where you have V2 also disappears. So Bernoulli's equation is simplified to P1 plus rho g y1 is equal to P2 plus rho g y2. Okay. So this one here, okay, is the same as what we've seen in lecture 12, where the pressure will increase with depth. So the higher the elevation is, the lower the pressure. And this form of the equation has an important implication. Okay, where elevation is high, pressure must be low. We've already seen that in lecture 12. But to understand how these equation operates, okay, so the left-hand side should be equal to the right-hand side. So let's look at an example. It's always easier to put in numbers to understand how the left-hand side should change if the right-hand side changes. So for example, we're given, say, the density is equal to 1,000 kilograms per meter cube. Say that's the density of water. G, that's gravitational acceleration, 9.8 meters per second squared. But for simplicity, let's just say G is equal to 10 meters per second squared. So it's easier to multiply by 10 rather than by 9.8. And let's say, for example, at this lower end, let's say that's P1, and let's say the pressure there is 10,000 pascals. And say the height is equal to 1 meter. Okay, we then change the height. Before we change the height, let's just do now the left-hand side of Bernoulli's equation, P1 plus rho g y1. Okay, so how do we solve the left side of Bernoulli's equation? P1, 10,000 plus the density 1,000 times 10 times the elevation 1 meter. Okay, so that will be 10,000 plus 10,000, and that will be equal to 20,000 pascals. Okay. Right. So each term in Bernoulli's equation refers to pressure. So each term will have a unit of Pascal. So the left-hand side of Bernoulli's equation with pressure P1 and height Y1 is equal to 20,000 pascals, right? Now, what if we change the elevation of the pipe? Okay. Such that, for example, the elevation is now 1.5 meters. Let's see how the pressure would change at this higher elevation. Okay, so the right-hand side of Bernoulli's equation, P2 is equal to rho g y2. Okay, P2 is what we want to find out, but rho, you have 1,000 times G, which is 10, times 1.5, okay, which is the new height. This one will be 15,000. Okay, so this equation says P1 plus rho g y1 should be equal to P2 plus rho g y2. P1 plus rho g y1 we solve to be 20,000. So 20,000 should be equal to P2 plus 15,000. So what is P2? What will be the new pressure when the elevation is 1.5 meters? Okay, so this whole thing, P2 plus 15,000 should also be equal to 20,000, right? These two things should be equal. Should be equal. Okay. Bernoulli's equation says that the cumulative pressure on one side should be equal to the cumulative pressure on the other side. And so for P2 plus 15,000 to equal 20,000, you need to add 5,000, because 15,000 plus 5,000 is equal to 20,000. So P2 should be equal to 5,000 pascals. Okay. Does that make sense? I think the key takeaway idea I just want to drive here is that where the elevation is high, the pressure must be low, and vice versa. If the elevation is low, then the pressure must be high. In order to keep both sides of this equation equal, if one thing increases, the other thing should decrease, so that overall nothing changes. Right? Okay, the second case is when you have fluid flow, but no elevation change. Okay, so how does Bernoulli's equation change when instead of having a static fluid and changing the elevation, we make the fluid flow, but we do not change the elevation. So it's simply just a pipe, a horizontal pipe, okay, where the speed of the fluid changes through this pipe. So Y1 and Y2 is the same because there's no elevation. And when Y1 and Y2 is the same, Y1 and Y2 can cancel each other out. Because say, for example, rho and G, they're just constant numbers, right? Density and gravity, they're just constant numbers. So say, for example, this is 10 pascals. This should also be 10 pascals, right? Because it's the same fluid flowing, so the density is the same, gravitational acceleration is the same, the elevation is the same. So Y1 should be the same as Y2. So if rho g Y1 is 10 pascals, then rho g Y2 should also be 10 pascals. Okay, and they appear at both ends of the equation. So if you subtract 10 pascals on the left side, you also need to subtract 10 pascals on the right side. In short, you can cancel rho g Y1 from the equation. And Bernoulli's equation reduces to P1 plus 1/2 rho V1 squared on the left side and P2 plus 1/2 rho V2 squared on the right side. So again, you have these two terms that are being added. You have, for example, P2 plus 1/2 rho V2 squared. And you have this equal sign. Same principle as before. If one value increases, the other value should decrease in order to keep a constant number. So the implication is that if the speed is large, the pressure must be small. So this is the same concept as before, except that as before, the elevation is the one that changes. This time it's the speed that changes. But if the speed is large, if you increase the speed, the pressure should decrease accordingly so that you still get the same constant number after you add these two. The cumulative effect of the change should still be should cancel each other out so that you should still get the same value for P2 plus 1/2 rho V2 squared as before. Okay. Right. So this case, the second case of Bernoulli's equation, actually allows us, explains many interesting things that we can observe. So for example, if I have a piece of paper here, all right, so essentially, yeah, air molecules are moving around the paper, right? But if I blow across the paper, okay, I blow on top of the paper. Okay. Right. So intuitively, we think that if you blow downwards on the paper, right, the paper should move downwards, right? Because you're exerting a downward force, you're blowing downwards. But instead, notice how if I blow on top of the paper or above the paper, instead of the paper going further downwards, the paper actually moved upwards, right? Okay, what's happening there? Why did the paper move upwards? So I blew air above the paper. So you have here a faster, so the air molecules above the paper were moving faster because I was blowing above the paper. And below you have slower speed. Okay, it's just still air below the paper. And the second case of Bernoulli's equation. So Bernoulli's, the second case that we looked at for Bernoulli's equation says that if you have a faster speed, then you have a lower pressure. And if you have a slower speed, then you have a higher pressure. Right? Okay, the higher pressure below the paper actually pushes the paper upwards. Okay, remember pressure is equal to force over area. So higher pressure is equivalent to saying there is a higher upward force from below the paper as opposed to a smaller downward force because of the lower pressure above the paper. And that's why the paper moved upwards when I blew above it instead of moving downwards. And it's the same thing when you have strong wind. Okay, the roof is actually blown off the house instead of collapsing downwards. Okay, it's the same principle. You have fast moving air above the roof, slow moving air below, and you have lower pressure above and a higher pressure below. Exactly the same concept there. So the higher pressure below pushes upwards, and so the roof is blown off the house rather than the roof collapsing downwards, right? Okay, Bernoulli's equation is also responsible for why we are told to drive, to put a large gap when we are overtaking a cyclist on the road. Okay, so yeah, so you have a cyclist that's moving slower, and you have you are moving faster. Notice that, yes, say the figure just shows a car and a truck, but it's the same principle. So you have these two vehicles that are side by side. Notice how there's a funneling effect of the air. So you have here smaller area, smaller cross-sectional area, as opposed to this bigger cross-sectional area. And continuity equation says that as the air flows through this smaller cross-sectional area, the speed will increase. So there's a high speed at this narrower area between the two vehicles. Because of the funneling, you can think of it as the funneling effect of the air. So high speed means low pressure. Okay. Compared to here, the air molecules are moving slower. So slow speed meaning high pressure. Right? And so because you have a higher pressure outwards compared to inwards, you have these two vehicles will tend to move towards each other there. So it's the same concept with you overtaking a cyclist on the road. You really have to take that distance seriously. So if you go too close, then you have this even narrower area between yourself and the cyclist. You have a faster airflow in that narrow area, and you have this bigger pressure difference that will pull the cyclist towards you. All right. The effect is even more dramatic if the object is moving, so one object is moving so fast and the other is at rest. So take a look at this video illustrating Bernoulli's equation. Yeah, so see how the pram was sucked into the airstream of the train. Then the train was moving fast, so very fast airflow where the train is moving. That means you have low pressure where you have fast speed, high pressure where you have slow speed. Okay? And the high pressure caused the pram to move towards the lower pressure part. Okay, yeah. So so there is science behind those rules that we need to follow. All right. Are we happy so far? I think the working Bernoulli's equation maybe will take some practice to get your head around with, but at least the concept, hopefully the concept is a bit more intuitive to understand. Yeah, so are we okay so far, and can we move on? Yep. All right, so let's just look at an example of how we work through Bernoulli's equations, how we work that equation. Looking again at the previous example of the blocked artery, where the area decreased by 33%. So we've seen in the previous example that if the area decreased by 33%, then the speed will increase by 50%, right? We worked this out earlier. Now, the next question is, how will the pressure change in the narrowed artery? Qualitatively, will the pressure increase or decrease? What do you think? Right. So we can assume that the artery is just along the same height. So you have here the normal artery. Yeah, let's just assume that the artery is just all horizontal. No, let me draw it better. Yeah. Okay, let's just assume that the artery has the same elevation, so we don't have to worry about the height. But then you have a narrowing of the area at some point because of the blockage in the artery. Okay, so we've seen earlier that the, say this is V1. Okay. And we've seen earlier that at the narrower end of the artery, the speed increases by 50%. So V2 will be 1.5 times V1. That's what we've seen earlier in the previous example, right? So the speed increased. Okay, what will happen to the pressure? Will the pressure increase or will the pressure decrease? Right? Let's look at Bernoulli's equation. It's the whole thing there, but the elevation's the same. So yeah, we can get rid of that term. So it's the same artery. Yeah, so you have this normal pressure on one side that accounts for the normal speed, and then you have the narrowed pressure there. Okay, so yeah, we've seen from Bernoulli's principle, right? If the fluid is flowing faster, then the pressure should be lower so that the cumulative effect would be the same. So the pressure must decrease. Yeah. Okay, does that make sense? Yeah. Okay. So it is this inverse relationship that we have. Increasing the speed should decrease the pressure, decreasing the speed should increase the pressure. So because the speed increased when the area became smaller, the pressure must decrease. But in the next question, the by how much will the pressure, what will be the new pressure, or by how much will the pressure decrease, and what will be the new speed in the artery, right? So the speed increases by 50%. Okay, that's what we've seen earlier. We've worked that out. So if the original speed is 0.16 meters per second, okay, that's the original speed in the normal artery, is 0.16 meters per second, that increases by 50%. So 50% of 0.16 is 0.08. Right. Okay, and so the new speed will be the original speed plus the 50% increase. So if you again increases by in mathematical speak, that's a plus, and then 50% increases by, that's a plus, and 50%, it means 50 divided by 100 of the original 0.16. And that's why you have 0.16, the original, plus the 50% of the original. That gives you the new speed. Okay, so an increase in 50% is the same as multiplying by 1.5, essentially. Good. And then for the pressure, so the pressure, we already know that the pressure must decrease, but by how much will it decrease? That's when we need to solve Bernoulli's equation analytically. So we need to solve this equation, and we want to find P narrowed. So this is the new pressure that we're wanting to find. Okay, so we need to rearrange to isolate P narrowed. So we want to find the new pressure in the narrowed part of the artery. Okay. So if you look at this equation, notice that it's just plus. So P narrowed is separated by this whole 1/2 rho V squared narrowed by a plus sign. Okay, so don't panic that this is a very long term. You can just replace this with for example, a dummy variable A, and you can just think of it as P narrowed plus A, and you're just getting rid of this whole term with the dummy variable of A. So to get rid of this, you need to do the reverse operation of a plus, which is a minus, right? So you minus 1/2 rho V narrowed squared on the left side, but you have to do the minus also on the left side. So 1/2 rho V narrowed squared. Okay, if you do that rearranging, then you have P narrowed is equal to the whole left side, P normal plus 1/2 rho V normal squared. You didn't have to do anything with the original left side because it's just there. And then you have this minus 1/2 rho V squared normal. So Bernoulli's equation might seem to be very long. If you're bothered by all these variables, you can just replace it by a dummy variable. For example, A. This whole term is A, this whole term is B, or something like that. So we know everything. It's just a matter of substituting the values. The normal pressure is 130 millimeters of mercury. We have to convert that to SI units. Okay, so let me just erase that part. Okay. Yeah, where's my conversion? Oh, it's actually just still millimeters of mercury. So 130 millimeters of mercury, and then you have 1/2 times the density of blood, which I think it was not given earlier, but this is some constant value that we will give you if you need it in the exam. For example, it's 1050, and then the area of the normal artery, 0.16. Don't forget there's a square. Okay, minus 1/2. It's the same blood. So it's the same density, and then you have the new speed in the narrowed artery. Again, don't forget there's a square. Okay, so the new pressure in the narrowed artery will be 113 millimeters of mercury. All right. Okay, any question about this solution? Are we happy with the solution? Yep. Good. Yep. Let me just tidy this up. Okay, so essentially that wraps up the lecture. I realize we've gone about 30 minutes over time, but didn't want to rush. These concepts can be tricky, especially with the long Bernoulli's equation that we've seen. Yeah, but we've looked at fluid flowing through an area. We defined the flow rate, and then continuity equation says whatever the amount of fluid coming in one end should also exit the other end. And then we've seen that the pressure changes when the elevation changes and when the speed of the fluid changes. And Bernoulli's equation relates the new pressure to the old pressure. Okay. All right. So how do we do this? Let me just